All right, welcome folks to day 3. This is Wednesday, June 9th, 2021. This is the Virtual Residency 2021 workshop, Introductory, Intermediate, and Advanced. And this is the first session of the day. We have a request for sharing the link where to find the recordings. So I'm going to tell you where to find the link, and I'll put it in the chat. If you just go to www.oscar.ou.edu/virtual residency, and I'm putting it in the chat now, 2021, go to that URL and just search for the word video, and you will find the link to the video page. And all of the videos from Monday and Tuesday are already uploaded. So I want to welcome our first speaker, Hussein Alazawi, from University of New Mexico, and he's going to be speaking on components of a research computing resource. So take it away, Hussein.
Thanks very much, Henry. Good morning, everyone. My name is Hussein Alazawi. I work at the UNM Center for Advanced Research Computing. And I think that this morning's session is the last beginner, intro session of the workshop, right, Henry?
That's right.
Yeah, so we will be discussing the components of a research computing resource, and you can see the name is kind of interesting and vague for a reason, which is everyone calls HPC systems in a different way. Plus, what we want to, our final goal is to support research computing in general, not only supercomputing. So before I even start, I would like to thank Henry for this workshop. I attended the first time in 2016, and actually this presentation has some material stolen, and you would see the references from the 2016 presentation when Dana presented this topic, Dana Branson. So I tried to build on it, and then we will move on. So a little about where I work. So we are a small HPC center in New Mexico. We are the first public HPC center in here, and I believe that we've beaten Sandia Labs to build the first B-Wolf cluster in 2000. So the center has been running for so long, I believe more than 25 years. But we are still at a small, medium-sized HPC center with 5 total employees as in technical staff, in addition to some admin. Our research is focused on mainly as an utilization of our systems is focused on nuclear, material science, physics, and biology, which I believe these are the top fields, maybe in most of the HPC centers, in addition to a vast variety of different topics, even humanitarian now and business, they are using the machines. So from there, we'll move to definitions, just what are these things? But before that, I would like to welcome, okay, so is this better?
The slide is partially cut off at the bottom. Can you go to reader mode?
I wasn't sure.
You're not in presentation mode. That's why either that or your screen.
To go into slideshow, or
yeah, either slideshow mode or reader mode.
I don't think it's cut off actually when you compare it with a little slide. I think it's fine.
Okay. Any recommendations on how to switch to reader mode? Is it in Zoom?
It's a little button on the bottom near slide mode, slideshow mode.
Oh, okay. Is this better now?
I think it's okay. Go ahead.
Okay. So here it says that resume share. Can you see the screen or no?
Yes.
Yeah.
Hussein, there's a bottom at the bottom of the presentation. It's a presentation mode, or you can just do slideshow.
Yeah,
yes, this one. Yes, this one.
okay, yeah. So I had an issue previously with slideshow. That's why. Okay, is this better now?
It goes actually to like smaller slides.
Yeah, that was the issue when I was in slide mode.
Okay.
When you press the swap display button, go back to the presentation mode and click on swap displays.
So I have two monitors here.
No. Yeah, click on the swap displays. Yeah, that one. Yeah, much better. Thank you.
Yep.
Okay, so I need to shift the screens because I have the chat open here on the side. Okay, cool. So what is HPC and what is a cluster? And before I start with this, feel free to type in chat. I will try to keep up with the chat. And if you have like an urgent question that I missed, just like open your mic and talk to me directly. So what is HPC and then what is a cluster? And the answer is, it depends according to Henry. So from here, we'll go to the next one, which is, what is a ship? So why do we build HPC systems? And what are they composed of? So if we compare it to a ship, we have all of these, like the hull and the keel and the deck, and you need all of these components to make it. But then what's the goal? It's like to go places. And this slide is stolen, as you can see. And from here, we'll go into a few definitions. So high performance computing is the use of parallel processing for running advanced applications. And you want them to run efficiently, reliably, and quickly. And then the cluster itself is just like a bunch of nodes. So I would say standard servers that they use in the industry as an enterprise servers. We call them nodes. They are all connected over networks. These networks can vary between Ethernet and InfiniBand. InfiniBand also includes OmniPath. It's supposed to be the same standard, and we will get to these shortly. And then now we got all the hardware, but we are still missing the software components. So we need stuff to manage the cluster, to get the cluster to run, and then after that, we need to install applications and get the users up and running. And all of that together makes a supercomputer. But like just looking at the components as they are, that doesn't mean much. It's just a machine. And then we are doing this just to get to the metrics, right? Like that's our goal, just simulating everything and defining a few more things. So computer simulation is a program that attempts to reproduce an abstract model. And then we want to do it in a virtual space instead of building it in reality. And the reason is usually cost and other stuff. Like sometimes we cannot solve these problems, or they can be so expensive or not applicable. So what we do is we would go into a simulation and just like run it. And then the cool thing about supercomputers is running in parallel. And to do so, we are running at the same time, simultaneously, millions of jobs at the same time by submitting and splitting them across all the nodes that we talked about. And we'll discuss more in detail later. And then when we utilize all of these problems, we cut the time. So like if you think in terms of minutes or seconds, how long would it take to process something sequentially? And then as you break it, how fast it can be. And the tinier and granular the components are, the more efficiency you would get out of your system and faster results. So in the US, the fastest HPC system till today is Summit. It's been holding for some time. These are some pictures that we stole from Summit, and it lives in Oak Ridge Labs. It's about 145 teraflops, and we'll talk about the history of these a little later. But then why do we want to do this? So we can solve tomorrow's problems, which we cannot study using today's infrastructure. So we have to bundle all of these machines together. And once we bring them together, they can act as one big machine. In the old days, when they started HPC, I will try not to mention any vendor names because I'm not endorsing anyone here. This is just like for the public community. So like machines, they used to be all one kind of big chip. And now what we are doing is just like going with a cheaper option, which is just like bring enterprise servers, connect them to each other and move on. Then another reason for HPC is bypass the limitations of Morse law. And for HPC, the computing power has been growing much faster compared to the PC itself, but it's still, we are limited by how much can we go, how fast, and how many transistors you can fit, and all of these things. So there are physics limitations, at least till today, that we cannot deal with. Then it also helps us with the research outcomes by going and processing so much data in a very short time. And then we can solve expensive and dangerous problems in simulations. So like think of nuclear explosions and experiments, or like now with the COVID situation, they were able to very quickly generate vaccines just because they had the genome map. And they started doing all of these testing. And you can see a lot of research where they compare like people who previously passed away before COVID, and then compare it to people who died because of COVID and see what's happening. So they can do so many different things at the same time. And then comes machine learning and AI and all of these things. And then all of this doesn't come for free. It has its own challenges. And the $100 bill, this has been a tradition for people who are new on the workshop. So this picture has been here in the workshop for so long, and I added a few things around it. So staffing, how can you compete as especially if you're a nonprofit or academic HPC center, how can you compete with the industry in keeping your staff who have all of these very advanced skills? And then how can you keep them happy? So I guess part of it is many of these people are in it for the research. Like they love to work with researchers on cutting edge machines where you are experimenting. Like, I think it's safe to say that HPC, academic HPC, is leading the industry on this part, because even vendors would work with universities to build the next systems and experiment using the cheapest possible way that they can, compared to going to industry where, like, enterprise or cloud services, where it would be so expensive because they cannot afford downtimes as we can do in research. And it's always funding. Sometimes it feels like you need to prove yourself every time. You have to go after grants, generate funding. So it can be very challenging between the machines, maintaining your power, space, and cooling. So now we are talking machine room and all the required resources that you will need, liquid cooling versus just like air conditioning. What kind of machine room? Is it a newer machine room or an old one where you have like raised floors and stuff like that? How are you paying for the space? Are you being charged for it, or is it covered by the university? Electricity is the same thing. Who's paying the bills? And then do you have to go into a cost model, or do you stay like providing free services, or is it just like a cost recovery? So yeah, and if you remember, like in the old 90s, I remember doing something similar to this, just like sticking a fan to a PC because, like, you know, Pentiums would heat up and start dying. And then, like, if we look at the cost and investment for the university, it's like return on investment. And if we think about this term as an industry, then we will be in trouble, because how can you measure the success? What are we bringing to the community, to the science in general, to the university itself? Like, how can you justify your existence? It will be so complicated. So I'm reading the chat in here. Yeah, so yeah, it's like, how can you justify your existence, all of these expenses, the electric bill, the space that you are holding. So this is a big challenge, and we usually show it by showing the research results, the grants that we are bringing, how it's impacting humanity in general, and then with specific topics, like think of global warming and the drought that we are having now these days in almost like all the west side of the States. And then our purpose is really to use computing as a tool to support the research. So sometimes we forget and we focus on the specs of the machines, like the cool network, like you got 100 gigabit InfiniBand network or 200, I'm moving to the next technology, CPUs and GPUs, all of these things. So you'd be thinking, is that how I measure it? Or what is my user group is looking for as a base? What they need is final results. Like sometimes they don't even care or understand at least what are we talking about. So it will be confusing for them. And I like this blog. So if you go check out, there is much more on that page over there. And then it goes to staffing, and we wear so many hats as staff. So you can be an HPC engineer who somehow fell into this position that you've never run an HPC system in your life before. But many of us started as a graduate student who was trained at an HPC center, and from there started to pick the experience and learn more about what are we doing and how are we moving forward. And usually you would go watch help tickets, look at them, see what's happening, and just learn by sometimes breaking things. And then we also do security, network, storage. And when you have a small team, sometimes it's the same person who's an HPC engineer. At the same time, they are doing the security, they are configuring all the networks, routing, switching, and the VLANs, and all of these things. And then comes the storage, and we have so many parts to the storage. We have a slide for that, and we'll go more in depth on it. And then at the same time, you are doing R&D on your systems, because many centers, when they go after a new grant, the staff themselves, like mostly they are expert in Linux, so they can deal with what's coming next. But at the same time, they have no idea what's the coming system. And of course, the mission of our mission as a center and the university itself, or that nonprofit organization, it matters a lot. Like it is the reason that we exist as a research center at the end. And sometimes you would find in small centers that you'd have the same people who are running the systems. They are also the CI facilitators and acting as application scientists. Somehow they manage to learn all of these tools and resources. They also negotiate and translate, because you would end up going to vendors to talk to them, to spec the next systems that you would want to buy based on your understanding when you talk to your researchers. So say that you have a condo model where you have a few different designs. You need to have like a base and some grounds where you can decide based on that, based on the needs of your people and the capacity of your center, on what kind of nodes can I buy? Like GPUs are cool, but then if you don't have enough power and electricity, can you buy these? Doesn't make any sense, or doesn't. Do you have the space? Now racks are getting more dense, so does your UPS support such dense racks or no? And then at the same time, you become an HVAC person. It happened a lot where, like in the middle of the nights, you would get a call from a sensor in the machine room saying that temperature is high or something, like a unit has failed. A UPS decided to go down, and like now you are running on just like on the whatever electricity company that is providing you the service, or if it's through the university. So I personally learned a lot, and my coworkers the same thing. So like I know a lot about HVAC now that I did not know about before. So the cool thing is you get to learn about so many things. And I think the experience that we gain as staff in academic HPC is great because you get to learn a lot about so many topics in a very short amount of time. And because of that, what happens later is that vendors start poaching these people and try to offer them more, or even other universities will try to hire these people to move them into higher roles or have them focus on something specific. So it is a challenge for academia to keep these people. So the solution, hire graduate students. We do this. So we almost have a matching number of graduate students to our staff who are working at the center. It helps a lot, especially when you have people who are confident and who used HPC before. Now, this term that you see on this slide, it couldn't be grad student. We had to hire a real person. This was said in 2016. The person who said it might be here. I'm not going to say names, but it was funny. And it's reality. Like many research groups who run their own little HPC clusters, they end up hiring a graduate student. So as a center, we hire them, we train them, and we keep them as just like as long as we can, if they're great. And sometimes we also developed another program, which is like ambassadors, which we would take a grad student for a semester or two, train them, and then you send them back as RAs to their departments. So we would cover their tuition and we would cover their salaries while working for us. And then when they go back, they will be covered by the department as research assistants to support their internal needs, which helps a lot. Like it's like a lost lead. At the beginning of the time, you would spend some time training these kids, but once they pick it up, they'll be great. Like they're a great resource and we depend on them a lot. But sometimes you find yourself that you cannot do this anymore. So that goes to, is it better to run research computing individually, like, when PIs keep machines under their desks? Or is it better to have it in one central location, regardless of it's under central IT as an enterprise IT with a branch for research computing, or if it's as a branch under the OVPR office, where they can just like focus on research as one unit for just like advanced research computing. Yeah, that's true. That applies to us too. So we hire grad students on as RAs and undergrads as just like as hourly, because I guess that's how the system of the university allows you to hire. So I'll move on here. And then as we talk about these systems, we need to understand the design. But before talking about the design itself and the components, how would an HPC system look like? I would want to describe it with kind of our left and right brains, how our left side sees the abstract things, and then the right side is more like responsible for being creative and all of these things. And to design an HPC system, you need both. You need to be systematic, looking at things, analyzing things, trying to predict what's happening or what's coming. And at the same time, you want to be creative about your design, and come up with the best ideas for your bugs that you're paying for that system. And this plays a big role in building systems. And if you go back and look at the top 500 supercomputers, it will be hard to say that every system matches the other. Like each system has its own nature, configuration, different set of applications. Even inside the system itself, sometimes you would find a divided project. So if you go to Exceed, for example, and look at the Exceed resources, which we will touch on later by the end of this presentation. So if you look at the Exceed resources, you'll be surprised how many machines are hosted at one HPC center, and each one is kind of specialized. So like now we are seeing pop-ups of systems that support, say, big memory nodes, or like large arrays of GPU clusters, or some kind of cloud computing with like some science gateways behind that. And I'm looking at the chart here. So yeah, the argument with IT happens a lot, and moving data over Wi-Fi is not ideal. So that's why there is the Science DMZ, which Doug talked about on the last presentation on, I believe, yesterday or the day before. And the Science DMZ allows you to build a special network within the campus network that is dedicated for research. And once you have such a network, you can even connect to like other nonprofit network providers like Internet2 or ESNet, and then go through that and connect to other universities over 100 gig. And I know that Internet2 did some experiments with 400G, and they have some white papers out there if you go and check them out. So just to look at the point of view here. So what HPC is, it's the creativity and analytical side. Then you bring the researchers, because you need to discuss all of this with your researchers and their needs as end users. And then your tech side to figure out the best way to deliver and fix the problems that the researchers are looking for. So the components of the supercomputer are very simple if you think about them. Compute nodes. So we have a lot of compute nodes. This is like the horse that runs all the stuff, do all the processing, and they come in different types and flavors. And then what kind of networking you are using, how many networks do you have in your cluster. Each HPC provider is different, and cloud providers are completely different compared to like on-site HPC centers. And then comes storage. We have maybe 3 or 4 different types of storage for HPC. And then you would need something to run your jobs and manage your machines. So that comes the management component of the cluster. And then what kind of software packages that you need. How do you install them? What kind of installers and all of these things? And how do you track change? How do you patch? So compute nodes, we call them pizza boxes. And you can see it's a laptop in a pizza box. And this term comes from the IT, the enterprise IT. So all what you need is really just a CPU, maybe a GPU, memory, depends on how much memory, what kind of optics, network cards that you want to put in your nodes. And then do you want it like to run in memory, or do you want to add disks to your machine? And then there are reasonings. So for example, at our center, we were running some machines without disks. But then what happened is we realized that we were running out of memory. So having local SSDs on our condo machines made sense, because the investment wasn't big once you split the cost on the different PIs as they go ahead and buy their different nodes. And then that little cost that we split makes the machine more efficient as you write, say, to a little SSD that is attached to the machine whenever you run out of memory on that. The compute nodes themselves can be different types. So many clusters, they have, say, like a majority of your nodes, like maybe 80% of the nodes, they have like standard CPUs. Sometimes centers would go and buy like 1 or 2 older versions of processors just because of trying to be cost efficient. Sometimes like how many gigahertz your processor is delivering is controlled by your power budget. So can you really provide more? Does it make sense to go with more processors, or does it make sense to go with more cores, or you want a higher computing power on that processor itself? Memory, same thing. There are different types of memory, so you would have to decide. Many of the HPC systems that we see, they provide big memory nodes. We call them in general big mem, and these big mem can be 1 terabyte, 3 terabyte, 12 terabytes. Like it depends on how much money you are willing to spend on this thing, and you want to make sure that it is efficient. So it doesn't make sense to have like a bullet train and run it on like an old railway lines, because you paid all of that premium price, but then you are not utilizing your computing power as it should be. So moving off the compute nodes, we have network. And one network that we don't see usually in industry, which working as an IT outside. So before I joined academia as an HPC, I worked in industry. I've never heard an InfiniBand networks in my life, or MirrorNet network before that. So it's a kind of different physical, and so it's like a different physical layer on protocol, and goes into different layers compared to the Ethernet network that everyone knows and uses. So like most likely your Wi-Fi, your Ethernet port in the office, all of like the internet port in the office, all of these are Ethernet. It has its pros and cons. So Ethernet is way much cheaper. There are much more vendors providing Ethernet network connectivity. And then the payback for this is latency. So you would lose on latency, which sometimes depends on your use case and your processing needs. This can be a problem for some applications. And then bandwidth, and that's how much data you're pushing on the wire. So when you hear 1 gigabit network, 10 gigabit, 40 gigabit, there is 25. So on Ethernet, you would find like I've seen in some places that they still have 100 meg at universities. So 100 meg, 1 gig, 10 gig, 25, 40, 100, 200. And then if you look at InfiniBand, it goes as in 40, 56, 100, and 200 gig. And of course, they're working on the next InfiniBand. But as of today, you can go and buy 200 gig IB networks, which makes your nodes kind of closer. So like, think about splitting a job across all of these hundreds or thousands of nodes that you have in your cluster to make them look seamless, as if they were running on one machine instead of all of these different separated little nodes. That's where the latency of the network comes as a big factor. And it becomes very important when you're doing like real-time analysis, like say some applications like seizure prediction in human or animal brains. As you try to predict something, apply some machine learning, and then after that you want to figure out or generate a response and send it. So you have less than milliseconds to respond to such a thing. And because of that, you would need something like IB network over Ethernet. Most of the cloud providers, they provide only Ethernet network. So if you are thinking about moving to a cloud service to do your HPC, you need to think about your applications and their needs. Do they need real-time data processing or no? Some vendors, they claim they have enhanced networking or stuff like that. But if you go back and look at the tiny grains, you would find that they are just pushing the utilization of the Ethernet bus as it is on the hardware level to split. So they are counting on not all the nodes being allocated or used at the same time. So think of like airplane ticket bookings, like when the companies, they overbook their flights just to make sure that their plane doesn't leave half empty or 70% of capacity. So that's what the cloud providers are doing with these resources. Or even if you have a private internal cloud, then that can be a different configuration. So after that comes storage. So people always would use as much storage as you would allow. So quotas exist to limit that. And without quotas, your system is most likely to be abused. So we mainly have home directories, Scratch space, and project space. And usually the home directories and the project space are enterprise storage systems where you make sure that you have redundancy, backups, long-term storage and archival plans to recover from, like now what we are seeing getting very popular is ransomware attacks. How do you recover from these things? So we have different scenarios. Usually we recommend our users to use their home directory only to stage their scripts and to push their final data into these home directories. And sometimes this applies to like say graduate students who are working on an individual project. And then project space comes handy when you have a big group or even 2 people or more needing to share data and access it at the same time. So this becomes a good resource. And so yeah, about backup, Scratch storage in almost everywhere is not backed up. I didn't hear of a backed up storage as in Scratch, but it has its internal methods of recovery. So I saw somebody, like they mentioned RAID, for example, in the previous comment. So almost all Scratch systems or storage systems in general are built on some kind of RAID, and there is parity. So if you're losing 1 or 2 disks as on the hardware level, you can still recover and restore, and your sysadmins will be notified, and they can go in and replace the hard drives. And it depends on your system. You can also auto notify the vendor who sold you that storage system, so they can ship you the drives immediately. So just like depends on your service agreement, how long it would take. Some of them, they have 4 hours window. Some of them, they would even ship you spares ahead of time to keep them on site. So when something like this happens, you just go and swap in, and that's it. And usually with RAID, you would just auto rebuild by itself. So no one would notice any downtime on Scratch space. Plus, if we are talking parallel file systems, because the Scratch file systems, they can be just network attached storage, or it can be a parallel file system. So with parallel file system, you still have so much redundancy, depends on the size of your system and how much you are willing to replicate. Now, the replication in this case wasn't meant for backup, it's meant for enhancing performance. So say that you have 1,000 compute nodes who are running the same job, accessing the same data set or say database that you are hitting. If all of them are beating on the same storage node, the traditional file system, that might steal your file system, or with the locking and all of these mechanisms, might be pointless to do your computing that way. So it would be better to load in memory and then come back and write later, or commit and save your codes as they run. In parallel file systems, you're reducing that number of locking by the factor of number of your storage nodes. So how many storage nodes you are replicating in your parallel file system, you're reducing it by that factor as in bottleneck. I will go back to the project space. So usually you want to provide a generous project space for your users. I've seen it range from maybe 20 gigabytes up to a terabyte. It depends on your center, on your budget, your charging model. And then for home directories, they try to keep them small. And when you keep these small, you are encouraging the users to utilize the project space and Scratch. And Scratch is the most generous space. I've seen centers granting from like, say, 0.5 terabyte up to maybe 5 terabytes. Some centers, they still don't have quotas deployed. And because of that, you can, some users can abuse the system. And when they do that, like all of a sudden you will find your file system is full, and then you would start receiving all of these help tickets of jobs crashing. And at first look, you'll be like, oh my God, something is wrong with my HPC system. But then you will look at it and like, oh, someone has filled the file system. Now, it happened to us a long time ago before deploying quotas, where we would even know our offenders. And what we did at the time, because our system wasn't capable, the old system of supporting quotas, we ended up scripting our own way to report and notify us ahead of time and notify the users that, hey, you need to be like a good neighbor and go and clean up. And then we have the resource manager next. And that's where people submit their jobs and they've missed something. And because of that little tiny thing that they've been waiting in the queue on, finally, when it comes to execution time, their thing is not running and it just terminates. So a resource manager oversees what kind of resources available for your cluster. So it kind of orchestrates internally the machines and the nodes if something needs to reboot and come back and re-image, compared to the scheduler that decides who runs when. And you can use your own queues. So you can have a general queue, especially in a condo model. So you can have your general queue where all of the people are competing, as in, say, first in, first out. You can customize your queues, for example, for smaller jobs. So like somebody who's submitting a very tiny job that you can squeeze, and then you can push these in between the big jobs. Different schedulers and resource managers. There are so many options. And that's another reason that there is almost no HPC system is similar to the other. Like even at our center, we have multiple machines, and sometimes you would find some machines are running in a different way, maybe because we refurbished that machine or built it new, or we figured out some mistakes and we decided to upgrade one of them. And then once we tested, we would move to the next one. And also what we do is, and many people do this, is like they would build a small cluster. And when they have that small cluster is just for testing, they would look into apply, it's like kind of the DevOps of enterprise side. So you try to deploy any of these things and test it and see how it goes before you apply it to a production machine. And then comes the HPC software, and there are just like general stuff. So I think some of the panels, the previous panels on this workshop, discussed like some kind of software packages that are custom for, like, say, a specific biology group, compared to general packages that anyone can use, or just like submitting your Python or C code or whatever it was. So this is more custom to the end user, to your researcher, and your admins need to adopt and learn at least the general idea of these packages, how to use them, how to install, track the changes. Sometimes people need different compilers. How do you keep all the versions? So this can be a big problem if the system is not that well organized. There are so many tools outside that people can use, and like SC is a great resource. Like they have so many panels just specifically on how to use like specific cluster management software packages. where you can manage your packages and track the changes, and even roll back if you ended up being in trouble for some reason. And then comes all the other components. And this slide just like includes everything else that we didn't mention above, as in the general 5 main components. So management and head nodes. Sometimes you would have one management/head node in your cluster. In big machines, you would have higher redundancy in these machines, just to make sure that if this thing goes down, your cluster is still up and running. You would need login nodes, and this also depends on the center, but like you can see more and more HPC centers now are moving to multi-factor authentication just because of all the attacks that are happening. With login nodes, your users would come from the outside, they would access the systems and they would be authenticated, and based on their authentication, their authorization level will be considered. And that's how they get into the system and they can submit their jobs. And then benchmarking your system. So benchmarks are very useful, but they also don't give you the exact performance of your system based on your needs. So it's always good to test your own codes, not only run like solid standard benchmarks, but they are good to compare in general. And then security and logging, that's very important. You want to know what happened. You have hundreds or thousands of users who are accessing your system, sometimes from a university computer, sometimes from their personal computer. You have no idea if that computer is infected. What do you do in that case? How do you respond? Do you have classified data? Do you have, say, HIPAA data or FRIPA data you are processing? So avoiding any trouble like that and locking your systems as much as possible is always recommended. It's seen in some HPC centers for some reason, maybe because we are research, they think it's okay to leave systems loose. So sometimes it happens where you would hear of a system that got compromised. And keeping logs helps you in going back and responding to an incident and documenting it, especially with compliance. Monitoring the utilities, this part is more about your machine room itself, like controlling the temperature, the humidity, the air conditioners themselves, the chillers if you have that, and then your UPSs if you're using UPSs. So you want to know everything that is happening, you keep monitoring it, and you have like auto calling systems that can notify your staff and have them come to the machine room to check and fix it and work with your like suppliers, whether it's internal or if it's like an external contractor who would come and fix your systems. Backup systems. And in this part, these backup systems, they're usually connected in the back end. So for an enterprise storage, this will be seamless, as in mirroring your data using snap mirrors, snapshots. And snapshots are amazing. Like, it's so helpful once you train your users to go back and look at a snapshot and restore their data from it. That helps a lot. Like, we used to get a lot of help tickets before, like, oh, I deleted this file by mistake, or my collaborator deleted this, I need it. So we usually take daily snapshots, hourly snapshots, daily, weekly, and monthly. And the more snapshots you keep, the safer you are, or more protected against attacks like ransomware attacks. Because say 3 months ago, you were infected by a ransomware that was silent for 3 months and you did not know about it until, say, today. What do? Do I go pay the ransom, or do I go and restore my system if I was keeping snapshots for, say, 5 months? Then I can go back, and what usually we do is like it's a crazy mode. So in that situation, and you saw what happened with the gas line company. In that situation, what you have to do is you have to go offline, disconnect all of your systems from the internet, start scanning and cleaning up everything. And then you need to disconnect your storage systems And after that, provide a temporary space where you can recover your data because you have no idea when you got infected. So what happens is I would go, say, back in time for a week. And when I go back for a week, I would scan my systems. If I still find that ransomware or malware on my system, I would roll back, say, for a month. And then you would go for 2, 3, 4, 5 months for how long you were saving in data. Snap mirrors are great for full recovery. So say your data center was on fire. If you had a snap mirror where you were mirroring your data to another site, like a different physical site, whether it's on campus or on like a peer campus outside another university or research center that you work with, or if you're just backing up to the cloud, which could be crazy expensive at this point once you decide to restore your data. So when that comes, Snap Mirror will give you a full data and you can spin it in minutes and have the same IP addresses and everything where you can provide your storage back to your users within minutes. Problem is it doesn't protect you from malware and ransomware attacks because the data is being replicated and synced like bit by bit. Now you can still have your snapshots backed to that external backup system and then you would be safe. And usually these backup systems are purchased at the same time and built at the same time that you built your enterprise, like home directories and project space. So the issue with that is, what do I do for long term? That's where, like I heard it yesterday, you go to your libraries. Like when it comes to archival, if your center doesn't provide archival services, and I know OU has a huge system that Henry was leading, and it's up and running. The latest expansion is up and running where you can back up your data to OU. It's very cheap. It's much cheaper than like industrial cloud services. It has its controls and you have to work within their protocols and standards. And Henry, you can correct me here. But it's a great system compared to the price and the service that it provides, and it helps you for long term. Tape systems are useful when it comes to long-term archival, or say a faculty comes and asks you to restore their data, or maybe they, like say that a research group came on board 5 terabytes of disk space on your system, then they receive more data and more data. Like we receive a lot of data from the DLA, the very large array, and it's like amazing how much data. It's almost 10 terabytes a week. So when you look at that amount of data, how can you keep all of it? So you need some method of archival because you don't want to lose this data on the long run, but at the same time, you cannot afford storing it. One option is to go on the cheap, dark side of the cloud. But then if you need to restore that data, it will be very expensive. Cooling systems, we touched on as part of the machine room. Air conditioners are expensive. Do you have a backup plan if your AC systems fail or your chillers fail? Like, what do you do in that situation? It happened to us before, luckily in winter, where we ended up opening the back doors of the machine room just to cool it down because outside it was way much cooler and it was almost freezing outside compared to inside. One incident, we used dried ice in a little room where the AC unit failed. So we just got dry ice, we put it in front of the racks just to cool them down immediately as we deploy the portable air conditioning unit. And then comes licensing, and this was discussed in one of the panels yesterday. So usually people would run a license server inside their center where they host so many licenses for the different research groups, and they control access to these licenses based on the needs or based on who paid for it. Like, you know, each license and application would have different terms and conditions on it. And then after that, and some centers also would ask their users to run their own licenses, which this is like outsourcing, offloading the service to the end user. But sometimes if the end user is not tech savvy or like involved in, say, system administration, that will be hard for them. It will make it more complicated. Web interfaces and science gateways. These are very useful, and there were already talks about them, and I think there is more material to come in this workshop to discuss these, where you can have specific places that you can run like this software in this specific version to be able to do this or that, say, service or process or simulation. And then comes data transfer nodes. These are tools that are used to move data between campuses or between different departments on the same campus. They are used as buffers to stage the data. And they have, sometimes it depends on the privacy that you're configuring on these. They can be only accessible from inside your campus or from over VPN, or they could be accessible and transfer data over the internet. That goes to your configuration. And then like one of the most famous tools that we would hear of is from Globus. So you can configure your own Globus gateways and you can transfer your data over that. And then comes the Science DMZ. And the Science DMZ, the name is interesting. And you know, I learned about it more from Eli Dart, who started that concept a long time ago at ESNet. And the idea, the name is kind of negates what it is. So a DMZ is like a network that has no firewalls and it's open and all of this. So the DMZ is really, it's a secure network, but it's secured in a different way compared to the enterprise networks. They secure it in a way that they keep the bandwidth and the throughput going and moving data fast within the safe areas that you have, whether it's on campus or across campuses. So you can work with Internet to, with their gateways that they have over the Science DMZ to move data safely between all of these different remote campuses or even continents. And then finally, this is how kind of a traditional HPC system looks like. So we tried OpenHPC, and in production, we kind of use parts of OpenHPC, and then we use other parts as of our own deployment and customization based on our needs. So I'll go back to how just like a standard HPC system looks today. So mostly running Linux. I've seen the other operating system maybe on 1 or 2 machines where they were experimenting with it, but almost everywhere it is Linux OS, some kind of flavor of it. You would have a login node where they would go in and just like people, that's how they can access the network. And then coming from the internet, it will be coming over Ethernet. So you can see that this slide is stolen from VMware. And I'm citing them, so it's not really stolen. And then you have an NFS, and this is kind of the old way of having home on NFS, because that's not the best, not the ideal scenario here. And then you have a parallel file system where you are serving your Scratch. And this is different from HPC system to another, even within the same center. And then the compute cluster is just as you see, it's compute nodes, mostly identical. We always try to keep the head nodes and the login nodes, especially the head node, identical to the compute nodes, like your basic compute node with the majority of number of that configuration. You would want to make your master node or head node as part of that configuration. And then you talk about all of these components, you have to go and buy them. And this slide is also stole from Dana's presentation from 2016. You can have the link and go there. It has more details about purchasing. So I try to just like fit a shorter version of that in here. So first you need to secure funding. So whether you would go after grants or you have a fixed budget with like a refresh cycle that comes, say, every 5 years. Most vendors, the lifetime of their systems go between 3, 5, or 7 years. After that, they would try to push you to refresh. They wouldn't renew support and warranty on the systems. And then what happens is, if you insist, renewing that support will be more expensive than buying a new system. Other centers deal and they make deals with vendors where they are leasing the hardware. And after given number of years, they would switch and swap that hardware for whatever price at the time they agree on. So you want to secure your funding, and you would want to go and design a system based on your researchers' needs. So again, here is where like it's not just about how many petaflops or teraflops or what capacity, what kind of storage. You need to understand the problem that you are trying to deal with and what you are solving. Are you building a system, say, only for biology problems? Or are you building a general system for everyone? Because if you're building it for a specific application or set of applications, then you can fine tune that system and get higher performance out of it. Then after that, you want to go to vendors and get bids on it. So you can go on a RFP, request for purchase, or you would do, say, an expansion to an existing system, and that's where the informally is. And in that situation, depends on your state and city and all the regulations and the university itself. How does your sole source would look like? What kind of justification? All of these things. And then you would go into a buying stage. And once you buy this system, it will come on site. Usually vendors will try to finish building the cluster within a week or so, sometimes even less, because Monday is very expensive. And sometimes you would opt in to receive engineers from the vendor, especially if you have a huge system. Or you would build it on your own, have your sysadmins set up all of these nodes and build them and set them up. Sometimes what you would do is you have your team set up all of that hardware and racks and all of that, and then say a week later, the vendor would send you an engineer to set up the cluster according to their standards. Because to accept this system, you need to run some kind of benchmarks and workloads. And sometimes running like a fixed benchmark is not very helpful, because that's just like very generic thing. So if you're building your cluster for a specific problem, then you better test it for that problem and type of workloads. And we always miss something. I mean, we are humans at the end. And when these purchases happen, usually the codes come very detailed, like it will be tens of pages. And if you missed one little tiny thing, then you might lose like a lot of on performance on your system. Like say you have multiple GPUs, if you don't have the bridges, the cables that connect, like it's a cable that maybe is $5. But if you don't have these bridges installed between your GPUs, then you'll be in big trouble. You'll be losing a lot of performance for really no reason, but a design mistake. In that situation, you would just bite it and go and buy these things and fix your cluster. Sometimes it's just a big cost, like it was like a real design mistake, and then that's where payback, that's like somebody will be responsible about it. So it happens. You just want to figure out how to fix that problem. And then we'll talk a little about cloud. So pros and cons. Cost. Moving to the cloud, the initial cost is usually cheap. Once you are deep in the cloud, it becomes so expensive. That's one thing. Then the other thing is recovery. If you have data in the cloud and you want to restore it or recover it or move it back, that becomes expensive too. Utilization. We did our own math at our center, and what we found is that if your utilization for your compute nodes is about 70%, then it's much cheaper to be running your own on-site HPC system. If your capacity is just like, say 10% or 15% utilization of your systems, then is it worth it? Because you need to think about electricity, the prime space itself, as in machine rooms and all of that, and the building, and then all the other things that come with maintaining a machine room. So is it worth it? So maybe the cloud is an answer for some research groups, or a hybrid model. Say you need a lot of resources, but you don't need them all the time. So I would go and I build my HPC system based on my understanding from the researchers on something that meets, say, their capacity for 90% of the time. And then if they needed more resources, we can configure the systems to do cloud bursting. So you push these jobs to the clouds temporarily whenever we have them, and then move back and just like kill these jobs once you don't need it anymore, or kill the instances, not the jobs. It is easy to build. Like looking at vendors these days, they already have pre-scripted cloud systems and architectures that they would let you go. But then comes compliance. And with compliance, that depends on your university, your funding agencies, maybe even the subjects of research studies. Like if you are working with specific ethnic groups where they have their own regulations of protecting their data, then you'll be surprised of you'd be surprised of how this data is so complicated to deal with. We were surprised with one of the systems that GPS locations became like a protected data, and we had to do like a whole masking thing and change a lot in the configuration before moving this data to the systems for processing. So there was a question about cloud bursting. So you can make the file system available if you are syncing your file system to the cloud. And again, uploading is usually cheap. Downloading your data is where it gets expensive. And then when you write your codes for cloud, sometimes vendors try to make it more complicated to, say, migrate to another vendor, but then the competitors would provide you with scripts that would help you to migrate to their own cloud. But then you would have like, unknown issues that you should expect some problems and some downtime. So as an investment, it can be a huge investment on the long run. But the problem with it is it's hard to track. So some universities have this issue where faculty would go and use, say, their non-university account as an email account to set up cloud services, maybe because they are trying to avoid compliance, or they just think it's easier and faster for them to get up and running with the research. So what do you do as an institution? You have no visibility to what's happening in that cloud or in the multiple, like all of these cloud services. So in general, if you want to virtualize your HPC system, whether it's a public cloud or a private cloud that you are hosting on site for some reason, say compliance, then you would have virtual hosts. So your servers, your nodes in the previous scenario, they will become hosts, and you can put many VMs on these hosts and load balance and utilize as you go. And this becomes like planes and tickets when you book on them. Computational science versus computer science, this comes a lot, where sometimes they think because you are a computer scientist, you should know how to use HPC. But really, computer scientists, they are trying to improve the computing resources themselves, improve the algorithms, the theories, and then how to bring it to life and apply it on the systems, versus utilizing the computing resources to do your science and research. So I don't think I have a lot of time, so maybe 5 minutes. So I would just like start skipping here. But think about time as in like, what is a trillion seconds? Like when you say teraflop or terabyte, like as in size or time, like a trillion seconds is like 32,000 years. So can you imagine all of these computing systems, the HPC systems, if they did not exist, how long would it take us to figure out our research problems? It will take forever. Now, your cell phone today is like a supercomputer from the 80s or even the 90s. So this is also like, it changes with time. And I will skip. This is just an explanation. You can go back to the slides and read about this. And then this one discusses the performance, and the math is very simple. Now, the history of as we are moving. So if you look in 93, the systems were in gigaflops, and then 97, we got to 1.3 teraflops. 2008, it moved to 1 point something petaflops, and then Summit comes and it gives like 120 something. I believe this is the older number. I think the updated benchmark number is like 145 petaflops, and you can check the numbers on the top500.org. And then what I've just found about recently is Leonardo, which is coming in Italy and through Euro HPC. And this system, as in compute capacity, it is 250 petaflops. That's what it promises, but they're calling it also pre-exascale. And they are claiming that it will provide 10 exaflops for the FP16 AI performance. So they picked a specific problem, and with all of these GPUs, they fine-tuned it, and their expectation is that this system would provide 10 exaflops for that single kind of use. But we'll see when or which year the next real, I say, because themselves, the Leonardo guys, they're calling it pre-exascale. So we'll see when the EXA system comes to life. Quantum computing. This is a cool picture from IBM from SC that I took in SC 2018. Talks about qubits and all of that, and I'm not going to pretend that I am an expert on this. And I'm sure there is many people who are involved in physics who can like do much better job. So instead of that, I will move you to this slide, which has a link, and luckily this was posted yesterday. So it's an amazing, it helped me understand more about quantum computing. So it's a good read, like maybe 10 minutes read. And then comes the HPC systems that are provided by Exceed. And Exceed is a great service. If you don't know about it yet, you should go check it out. There is the Campus Champions, who was spun through Exceed, and now its own nonprofit organization that represents the community. And I actually joined the Champions because of this one workshop, which we are attending right now. So it's a great chance for everyone to go and check it out and communicate maybe with the leadership team or the contact person for the Campus Champions. And there is a mailing list that sends a lot of resources. And as a Campus Champion, you would receive like some limited time on the different Exceed HPC systems. Now, this time that you would receive as in CPU hours and storage, it's not designed for the Campus Champion. It's not designed to do people's research, but to run like full experiments, but it's to test it, to see how they can fine tune their codes. And based on that, they can go and submit like grant requests to get more access and more CPU hours or GPU hours or storage on the Exceed resources. And each system has its own documentations and support team and all of these resources. So this is a great service that you can access. And that was my last slide. So if you have any questions, feel free to ask. And I believe that we have 1 minute to go. So Henry.
Yep, we got time for basically just one quick question, and then we'll need to wrap up.
Okay. So maybe I will go and look at the chat.
Looks like a question just popped up in the chat.
Well, I personally am not aware of this database, so maybe somebody from the attendees can answer this. And I would say, since I'm looking at numbers and prices, you would look at your investment. Do you have the staff who can run these systems, or do you want to outsource it and go to like an external vendor where you are dealing with this, or is it worth hiring somebody, or do you have the expertise on your team to deal with it today? So with that, I would like to thank everyone. The slides are available on the workshop website, and feel free to reach out to contact me. You have my LinkedIn here. And I'm so happy to be part of this workshop. Henry worked so hard to prepare for this, like QX on it for like months. It's like his baby. So I'm very proud to be part of this, and thanks, Henry.
Well, thank you, Hussein, and thank you for a terrific talk. And also, I should say that at a very young age, I sent my baby out into the world. So now it's all of our baby, and I'm very proud that this particular village is raising our child together. All right, so let's see. So we have a break of just under 30 minutes. And then we will be back at 1/4 till the hour. So that's 11:45 Eastern, 10:45 Central, 9:45 Mountain, 8:45 Pacific. And please forgive me, folks in Hawaii. I think it's something like 6:45 in the morning for you when we run this next session, which will be facilitating cloud computing. And that's going to be a wonderful panel. And we're looking forward to that. So that's in 28 minutes. We'll see you then. I will leave the session open and I will turn off recording, and we'll see you all in 28 minutes, 27 minutes, whatever it may be. See you soon.